My name is Prayag. I'm a data science engineer at UP42. And in the next 20 minutes, I'm going to walk you through how to use UP42 platform, download the dataset, and train an unsupervised network in the context of Copernicus master program. So in the following 20 minutes, it will be divided into two separate sections. One where we will see an example of how to use UP42 platform to create a training data set, as well as followed by how to train a simple vanilla GAN to showcase how this data set from UP42 platform then can be fed into our neural networks. The requirement for this one is to have a UP42 account on our platform and have authentication keys, as well as an UP42 SDK. If it's not installed, we can install it. Here I have in my environment installed, so I will just import UP42 SDK along with other libraries that we're gonna need it. Now, from the developer settings on the platform, you can retrieve the project ID and project API keys, which can be set into a config file, and then we authenticate to the UP42 platform. Now, as we can see that the authentication is successful, and now we can initialize the project. Now on UP42 platform, the way it works is a hierarchy of objects. So the first top level object is the project. A project can contain workflows, and the workflows can have multiple tasks. So as we initialize the project, as it's successful, now we can create a workflow. I'm going to name it a tiler, since we are going to tile our data sets. And the task that I'm going to use, or the data set that we are going to use for this presentation, is going to be Sentinel-2 dataset, a visual product, meaning RGB as a data source, and followed by a processing block called tiling. So as it is loading the project and fetching the dataset from the platform via API, as soon as it finishes, we can add these tasks that we mentioned earlier to the workflow. So now the workflow has this task. As you can see, the parent block task here is the Sentinel-2 L2A GeoTIFF visual product, RGB image, and followed by a tiling block. Now, obviously, we need to define the parameters upon which we will search the image first, and also then tile it. Now, as it is the case with many of the neural network deep learning trainings, that the network expects tiles or patches, as we call it, in the 256 by 256, sometimes 512 by 512 height and width. So in this case, I'm going to generate tiles of 256 by 256. And of course, the image being RGB, therefore the number of channels are going to be 3. Now, another interesting part here is the augmentation factor. Currently, it's set to 1, but effectively you can set to 2 or 5 based on your requirements, which essentially puts a pixel offset into the generated from the image, and effectively you can have more patches out of a small image. Instead of a regular grid, you can have an overlapping grid so that you have more training data set, which is one of the very interesting and useful component when you don't have enough training data set and you might want to create more data set, other than augmentation techniques that are quite commonly used in the deep learning industry. Same goes for the fetching the image, Sentinel-2 visual product. I have defined the max cloud cover to 2 so that we ensure that our images are as much cloud free as possible within this given time range. Now, I will run. Now on the UP42 platform works on the credit system. So you can also estimate the job before actually launching the job so that you exactly know how much credits you are going to spend. So when I launch the estimate job for a given workflow for the parameters that we have just defined, So we can see that we are going to consume 2 credits at max. Now, ideally, you want to run the job and also download the results. However, since this can take some time, image is big, area is big, and there is patching also takes little time. So to save the time, what you can also do is that I've already run a job where I can retrieve the job ID from the previously run the job and just download the data set. Now also, the data set is quite huge, so the download obviously takes a little longer. Therefore, I have commented it out here, and I've already previously downloaded the data set. So I will load the job results, the directory where I stored the download for the images. And now I'm going to read the TIFF files into an array. And as we can see that we got 4,225 images from our job. Let's have a look at it. Now, these are the GeoTIFFs, meaning that they are not regular JPEG or PNG. They are 8-bit TIFF files, for which we will use Rasterio, the pretty standard library to manipulate and access geospatial remote sensing images in Python. Now here I'm going to reshape as image because Rasterio originally reads image as channels first, followed by height and width. But our neural network, I tend to prefer to feed it into channel last format. So I will read the data set, and let's have a quick look how the image looks like. And here is an image from one of the patch 256 by 256 from the Las Vegas, Nevada area. Just to check, if I do data.shape, it's a patch that we expected from the tiling block parameter. So now that we have all the data set, all the data that we need, let's jump on to the actually training and how you can use this data set to train your model. Now, one of the requirements for the Copernicus master program is that to use the GAN. So in this example, we are going to train a deeply convolutional generative adversarial network on Sentinel-2 dataset in an unsupervised manner to generate synthetic dataset. Now, taking a step back, what is GAN? So basically, it's a concept derived from a game theory domain. It's basically a generative adversarial network. It's a class of machine learning frameworks originally authored and introduced by Ian Goodfellow and his colleagues, where 2 neural networks compete with each other in a game, and basically one's gain is another one's loss. In a simple words, for an analogy, I like to think it in a sense of that there is an artist who is a painter, and there is an art critic. And it's a game between these two where a painter or artist creates an art, and the critic's job is to say whether it's a real image or a fake image, whether it's a forged painting or it's not. So generator network basically generates, as the name suggests, and the discriminator is the critique in our analogy. So to begin with, we import all the libraries that we need. We are going to use Tensorflow framework here to train our model. And one of the examples for use case for generating a synthetic imagery is, let's say that you want to train a model, a classifier model for detecting ships in an image. Now, it's pretty difficult to collect the ship's data set. For example, open water ships are very hard to take an image of, or most of the images that you might find is the images close to the harbor or parked next to the port. Now, in order to have the more diverse data set, you can use the generative networks to create a synthetic image that has a shape like a ship, or actually a ship. And this then can be a additional input to the classifier network so that we effectively increase our data set. So here I will load the images that we previously downloaded, and just checking it again that if everything works as expected. So let's just quickly check the shape of the data and the data type. It's a uint8, meaning that the values will be between 0 and 225, and a sample image. Okay, everything seems to be fine. Now, before setting up the neural network, the authors of the DC-GAN paper had some recommendation in the paper for the architecture guideline for more stable DC-GAN. And these guidelines are basically replacing pooling layers with the strided convolution. In a regular deep convolution network, it's pretty common practice to use max pooling or average pooling layers, but instead, for discriminator, we use strided convolution and fractional strided convolutions for generator. Also using batch norm, because then the batch norm brings the mean of the data set to 0 for both generator and discriminator after each layers. Also, there are no fully connected hidden layers when you are using deeper architecture, and using ReLU activation for generator, except for the TAN-H. Now, this is important because TAN-H activation gives you returns the values between -1 and 1, which we will see it in a moment, why it matters. And also using leaky ReLU activation for the discriminator for all the layers. So with that, let's import the TensorFlow library. In my environment, I have TensorFlow 2.3.2. Import the libraries. Now here, I'm setting up a buffer size to 2000, and batch size to 16. Now this buffer size is basically used for creating a training data pipeline to have the buffer when loading the data set. And batch size, as we know, is the standard hyperparameter for training any neural network. It can be changed to 8, 32, 64, depending upon your machine size. Now, before training, we need to define the data pipeline. And here I have defined some of the functions which loads the data set from a given directory, as well as the train test split. Here I'm splitting 80-20. It can be 70-30 as well. Now, as I mentioned earlier, we have here TIFF files, and we already saw how we can open it with Rasterio. And here, interestingly, since our data type is uint8, normal practice is to divide it by 255, but here we are going to standardize the image. Why? Because then the values will be between -1 and 1, which then corresponds to TAN-H function that will be used in the generator last layer. So this is an important aspect to keep in mind. Now here's a simple preprocess function which converts the image array, NumPy array, into TensorFlow tensors, which is required. I will load the data set. And here I have almost 16,000 images for train and 4,000 images for the test. Now here I'm using a TensorFlow dataset API to create a dataset pipeline. Now one of the advantages of using this is that it has out-of-the-box capability to parallelize your training code, meaning that with this TF data experimental auto-tune, it allows to use as many cores as possible. And also when the tensors are on GPU, being processed on GPU, the CPU doesn't stay idle and vice versa. So it's a powerful API So we are going to create a training data set. Now here we don't need to create actually test data set because our task is unsupervised task. So let's quickly check if everything worked correctly. Now coming back to the unsupervised scenario, since we don't have any labels, we can learn good intermediate representation that can be used for a variety of different tasks, as I mentioned with the ship example. Now, we can also reuse the parts of generator and discriminator networks as feature extractor for many other tasks as well. So here we can see that the batch size is 16 and our shape is 256 by 256. So everything seems to be in order for our training to start. I will define the weight initializer, which is a random normal with a mean at 0 and standard deviation of 2. Now here I will define a generator model. So what is generator doing? Essentially, it takes a noise vector or noise tensor, and then with transpose convolutions, we are increasing the sizes of the after applying each of the transpose convolutions, and of course batch normalizations and the activation function. So at the end, after 5 upsampling, we reach the image size of 256 by 256 by 3, which is what we want. So I will execute the method, create a generator model, and let's take a look at the summary, which will make it more clear. So based on the dense layer that we pass with the initial noise vector, we reshape it to 16 by 16 by 512 channels. And then after applying another strided convolution, transpose convolution, we double the height and width, so on and so forth, until 256 by 256 by 3, which is what we want to achieve. Now, it's about the noise vector is about peeking into the latent space distribution. So now, since we have created the generator model, oops. Let's take a look. So right now, the generator model is not trained at all. So it's returning a noise, which is expected. And we will see later on how it looks like after we have trained to some epochs. Now, equally, we will define a discriminator model. And remember, discriminator is the critique here. And critique's job is to tell whether something is real or something is fake. So here, to know that the last layer is a dense layer with only one neuron with the activation sigmoid, meaning that it's bound to return true or false probability. So let's quickly evaluate the discriminator as well, that whether it's doing as we expected, because right now it's not trained. So expectation is that without training, the discriminator is going to make a random guess. And when executing, we can see that the output is 0.47, which is close to 50%. So right now, discriminator is just guessing, which is obviously because it hasn't been trained. So we define a loss function. Here we will define a binary cross entropy because we want to have true and false. Equally, we define the discriminator loss and generator loss, followed by optimizers. Here we are going to use Adam optimizer with the learning rate of 0.0002, which is the recommended values from the paper itself. So no change made here. Also, as those who are familiar with TensorFlow, it's always nice to checkpoint to your training, so that whether if you want to continue or machine collapses or crashes, you can retrieve your training and all those hours don't get wasted. So I will define a checkpoint directory. Now for this example, I'm just going to train for 10 epochs, because since the dataset size is very huge and we want to save some time. So here epochs I'm setting to 10. Now noise dimension, which is the input vector, is to set to 100, and number of examples to generate is 16, which is equivalent to the batch size. All this can be changed according to your requirements. Now here, since we are dealing with two networks, we have to define a custom training loop. And here we are using a tf.gradient tape, which will record the weights and biases as the images pass through the networks. And at the end, we return the loss of both discriminator and generator. So this is a custom training loop. Also, we define some auxiliary functions because we want to know that how the model is doing intermediately as it is training. So this is simply just makes a prediction and calls a model on the input and just saves the images. Same goes for metrics. We will, after certain epochs, we want to see how the model is doing, and we will save the metrics as well. Now comes the train loop. Train loop, so as most of the things we have already defined, it will iterate for given number of epochs and run the train step, our custom training, and also return the loss. So now we will launch the training, and this may take some time. Okay, so here, after first epoch took about 250 seconds, around 3 minutes. And we can see the first results. Of course, the training just has started, and it will take some time until the model learns all the nitty-gritties of the data set. But I have already pre-trained the model until a few epochs, and I will show some results. So I will pause the training for now. And also there is a code for saving the model. So I have already trained the model for 150 epochs, which I will load it from previous state. I initialize a new noise vector, and let's check predictions. So as we can see, the model has generated decent synthetic images. Some of them, like the one in the top right corner, it could be mistaken even for human eye as a real image. Of course, there are these artifacts. There are strategies, ways to remove them, or also longer training, and eventually these artifacts disappear. However, this is to just give you an idea of what this generated synthetic image could look like from a very simple data set in Las Vegas. And yeah, that's it. I hope you have so much fun solving the Copernicus Master Challenge, and we are looking forward to your submissions. Thank you.